All right, hello and welcome. In this video, we're going to look at how to calculate out the frequency and the output voltage of this RL low-pass filter. We know it's a low-pass filter because of the topology of the circuit. So from our voltage source over here at the beginning of the circuit, we see that we have no choice but to go through this inductor to get to where we call our output voltage, right? So that's going to lead us out to whatever else is in the next stage of our circuit. And since this input voltage has no choice but to go through this inductor, we know that that inductor does not like high frequency and it allows lower frequencies. And so this means that this is going to be a low pass filter and all high frequencies are going to get stopped before the inductor there. And so you can tell based on your topology on what type of circuit you're working with, low pass, high pass, or band pass. So in this case, we have an inductor and a resistor, and if we're looking for frequency, we got to focus on the components that we have in the circuit to figure out our time constant, because our frequency equation says we have well in this case FC for our cutoff, is equal to 1 over 2 pi, and then whatever time constant we're working with. In this case, we have an inductor and a resistor, and so we're going to stick with our LR time constant, which is our L divided by our R. And so we have two other time constants that we've been working with. That is the square root of L over C, and then the RC time constant where we multiply resistor and capacitor together. So it just depends on what you have in your circuit, what you're going to work with as far as time constants. So we can calculate this out, 1 over 2 pi. So we'll type that in, 1 over 2 pi multiplied by our inductor, which is currently in millihenry. So we're going to move that out. So 3.6 gets 0.0036 divided by our resistor, which is in kilo ohms right now, so we'll move that out also. That's 1,800. That goes the opposite direction, 1800. And that gives us a pretty large number. We're going to keep 3 digits of this. All numbers you want to keep 3 digits of. So in this case, they gave us 79,577, and we'll round that up to 79,600, 79600, and they want it in kilohertz. And this right now is just in normal hertz, and so we'll move that decimal point over by 3 and put it into kilohertz. 79.6 kilohertz is our frequency. So that's where we expect this low pass filter to be responsive at, 79.6. After that, we want to go after our output voltage, and our output voltage at cutoff is going to be the voltage that we see at this output line here, and that's actually the voltage across this resistor. Right? And so since this component is in series with its inductor, technically, right, we have no choice but to go through there to get to ground. We're going to use a voltage divider equation. And so that's our want over have equation. Whatever we want goes on top of the circuit, or goes on top of the division. Whatever we have goes on bottom. And in this case, we have our resistor on top. And so we'll set that up down here. We'll say R divided by our Z value, our total inductance for the circuit. And this is going to be our V out equation. And then that whole thing gets multiplied like our voltage divider equation, want over have multiplied by our source voltage, so Vs. Right, so we need to figure out our Z value because we know what our resistor is. It's 1800. We can rewrite this 1800 divided by whatever our Z value is multiplied by our 10 volt source. Right, so we need to figure out Z. So let's do that up here. Z equals, we know that our Z is in rectangular form. We can write that in immediately. We can say that we have our resistor of 1800. And that is at a plus or minus. The plus is going to come from this inductor, so we know this is going to be a plus J, and then whatever our XL value is. And we don't have that XL value, so that is where we are going to start here, is getting our XL value. Since we just found our frequency up here, we can apply that. We can say XL is equal to 2 pi FL. We have our our frequency and our inductance value, so we'll just type that in, 2 pi multiplied by our frequency of quite large, 79,600. And then that's multiplied by our inductor value, which is quite small, 0.0036. And that gives us an XL output of 1800. It's interesting. And that's in ohms, right? And so we kept 3 digits of that one. So we can replace this in our Z equation. We can say XL is now equal to 1800 also. Both of those are in ohms. We'll flip that over using our rectangular form. None of this output over here is requiring our phase angle, right? We're not focused on phase angle for this one. We're focused on just the output. So we'll just do our magnitudes. And so in this case, we'll take our square root equation to get our magnitude for this value. We'll say 1800 squared We'll add that to 1800 squared. And that gives us this number here as our magnitude. So our z value is equal to 2,545. We can probably round that off also, but we'll keep the whole number, 2,545. We'll put that in for our z value down here on the bottom. So let's erase this z now that we know it. We'll say that that's going to be our 2,545, and we can plug that in our voltage divider equation here. 1,800 divided by 2,545. So that is our distribution of our voltage, and then we'll multiply by our voltage source, which is 10. And we'll get an answer out here. That is 7.07 volts. So that's what we expected our output, 7.07 volts. All right, and let's check that. Okay, let us know if you have any questions.